Hello guys, welcome to video 3 for week 10. We're going to continue our discussion about confidence intervals. So far, all of the confidence interval stuff that we've done has been about proportions. In other words, for categorical data. Remember, proportions are how we summarize categorical data. Hair color, nationality, etc., etc. Anything that's a category, we talk about proportions or percentages of those things. But, of course, not all of our data is categorical. A lot of it's quantitative too. So we want to talk about this same technique using quantitative data. We summarize quantitative data using averages, or in other words, means. So we need to think about making confidence intervals for population means. In other words, mu. So just like we use p hat in order to approximate p, we use x bar, the sample mean, in order to approximate mu, the population mean. The technique is very, very similar, but since we're talking about a different kind of data, we've got a different set of tools. Fortunately, you guys know that the central limit theorem works for both means and proportions. The central limit theorem tells us if our sample size is big enough, both x bar and p hat follow a normal distribution. So the technique works pretty similar for both of them. There are a few little details we're going to have to iron out, but the basic idea is the same. So let's think a little bit about the formula. You guys already know the idea for a confidence interval, so I'm going to dive into thinking about the actual math behind this stuff first. Remember, all confidence intervals have the same structure. We saw this last time. All the confidence intervals we do in this class, including the ones from last time and the ones we're about to do, have this same structure. They start at a point estimate. That's a single number that estimates the population value. And then they've got to have a margin of error, the stuff after the plus or minus. All of this stuff, that's the margin of error, everything after the plus or minus. There's two important pieces to that. We need a critical value. That comes from our level of confidence. Critical values are the cutoffs for the middle 90% or 95% or 99% or whatever. And then we need the standard error. That's the standard deviation for the sampling distribution. Here, the standard error for this stuff is sigma over square root of n. And we've seen that before. That's exactly what you did in week 8 when we talked about the sampling distribution for x bar. If that doesn't seem familiar, I really recommend going back to week 8 and reminding yourself of some of those examples. They're the ones that you just did on the quiz recently, and I thought everybody did great on those, so I know they're up in your brain, but make sure that seems familiar because we're going to talk about it today. So if we put all this stuff together, if we use this structure for x bar, that gives us a formula for the confidence interval. Warning, this isn't the final answer, but it is the starting place. Our point estimate is x bar. Critical value is z. And our standard error is sigma over rad n, just like before. There is a little problem with this, though. Let's talk about that. So, what's the problem? Why can't we just use that formula and call it a day? Well, here's the thing. In that formula, let me scroll up a little bit really fast. In that formula here, that stuff right there that I just highlighted, that's the problem. Sigma. Think to yourself for a second, wait a second, what is sigma? Sigma is the population standard deviation. But hold on. The whole reason we're doing this technique is because we're trying to approximate what's going on with the population. We don't know these population values. We don't know mu, the population mean. So why the heck would we know sigma, the population standard deviation? We totally won't. That's the whole reason we've got this stuff in the first place, because we don't know what's going on with the population. So crap. That means there's something in the formula that we don't know. Now there is a solution, and it's not too hard. Since we do know what the sample standard deviation is, let's use that instead. And remember, sample standard deviation, I never make you guys compute this by hand, but it's pretty easy to compute. Here in R, for example, you guys have used the SD command before, and just as a little example here, I wanted to give you the standard deviation of the sepal length from the iris data set. You can see it's 0.828, blah, 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 blah. So this stuff is easy to find. There is a price to pay, though. S is only the sample standard deviation. So it's probably not as good as the population standard deviation. And that's true. If we use S, the short story is it's just not as good as sigma is. Sigma is the population value. We wish we knew that. We're replacing it with something that's probably not as good. It's definitely not as good. And it turns out that actually changes the shape of the sampling distribution that we're using. Oh no, that shape is really important because that's how we find these probabilities. There is good news. Even though these problems don't follow a normal distribution, they follow a very similar distribution called the t distribution. It's called the t distribution. It's lowercase t. And it's really similar to the normal distribution, but it's used in this special scenario where we don't know what the population standard deviation is. So in practice, when we're doing these problems, everything works pretty similarly, except instead of looking at the z table to get your critical values, you're going to look at the t table instead. So no big deal. It's just a different table. Or in R or other software, it's just a different computer function that you use to find the critical values. So let's take a look at the t distribution to get a feel for what's going on there. Using the t distribution. The t distribution is very similar to the normal distribution, and in fact, to the human eyeball, to our eyeballs, you can't even really visually tell the difference. They look very similar. They're both bell-shaped, they're both symmetric, and they're both centered at 0. Let me just show you in your textbook. Your textbook has a t-table. This is the t-table from your textbook, and you can see that's a picture of the t-distribution right there. Looks pretty darn similar, right? Remember, these things are really easy to find from the table of contents. I just scroll back up to the very top, come down to the table of contents. It's distribution tables. The first one is the z table, and I'm scrolling past that one because we want the t probability table. You can see there's even like a little lecture here that shows you how to use the table. Here, I'll just bring up the table today because that's what we're going to do. So there it is. It looks really similar. Same bell shape, same symmetric about 0 sort of situation. There are a couple of important differences, though. First, and most importantly, the t distribution has thicker tails. The t distribution has thicker tails than the normal distribution. It's hard to tell when you're just looking at a picture of one of them, so let me show you another picture. Here is a picture that compares both the t distribution and the z distribution. They're not labeled on this graph, but you can tell the z distribution is the blue one. The normal distribution, or the z distribution, is blue here. It's got skinnier tails, they're shorter on the outside, and the variance isn't as big. It's more concentrated to the middle. The t-distribution is the red one. The t-distribution is the red one, and you can see on the outsides, those tail areas are thicker and bigger. That has a few really important consequences for everything that we do with the t-distribution. Another important difference between the two is the shape of t. Let me clarify. The shape of t depends on the sample size. We're using the sample standard deviation, so samples are an important part of the t-distribution. In this particular context, we call it degrees of freedom. Degrees of freedom is basically the same thing as sample size. It's n minus 1. There's some fancy math reasons for why it's n minus 1. But intuitively, if you think about degrees of freedom as being the sample size, you're not wrong. That's basically what it is. So since the t-distribution does depend on sample size, whereas the normal doesn't, that means the t-table in the back of the book has to be rearranged a little bit in order to accommodate this. We can't have a different table for every different degrees of freedom, so things have to be reorganized a little bit. Let me just take a look with you guys right now. Here's our t-table in the book, and you can see, do you see my cursor? There's a whole column here for degrees of freedom. That's what the DF is for. You can look up degrees of freedom, and then there are some various cutoffs in the table. Works a little different than the normal distribution. I'm just going to show you a couple of examples, and I think you'll get the hang of it. Let's do a couple. How about number 1, for example? Number 1 says, if we're taking a sample of size 34, then what are the cutoffs for the middle 95% of the distribution? Okay, let's think about it. First, if we've got a sample size of 34, that means our degrees of freedom here, df, it's always n minus 1. That's 34 minus 1 here, and of course that's 33. df equals 33. So that's the row on the table that we're going to look at when we find our cutoffs. Now we need to think about the tail area. And you guys have seen this example a bunch. If there's 95% in the middle, my head is the middle of the curve, that means the two tails each have to have 2.5%. There are a couple of different ways of thinking about that. The one tail area is 2.5%. If you think about both of the tails together, the two tail, of course that's got to be 5%. Makes sense, right? If there's 95% in the middle, then the two tails together have to have 5%. Each one specifically has 2.5%. Later on, when we do hypothesis tests, it'll be more useful for us to be careful about which one's which. But here, it kind of doesn't really matter. Either way you want to think about it, it's exactly the same information on the table. So let's go look it up. We've got degrees of freedom 33. And our one tail area, let me scroll down. Here's degrees of freedom 33. You can see it right there. Degrees of freedom is 33. And my one tail area is, you can see these things are the same right there. One tail area is 2.5%. That's the same thing as having a two tail area of 5%. Either way you want to think about it, totally the same thing, right? And if I match that up, that gives me a cutoff here of 2.03. And that's it. In other words, the middle 95% of the t-distribution, when degrees of freedom is 33, is between negative 2.3 and positive 2.3. Here, cutoffs. Negative 2.03 and positive 2.03. One's on the left and one's on the right, i.e. the middle 95% of the t-dist, where degrees of freedom equals 33, is between t equals negative 2.03 and t equals positive 2.03. And that's it. That's all there is to it for reading the t-table. Pretty easy, right? It's got a different structure. Be careful, don't get confused with the z-table. It has to be set up differently because the t-distribution has degrees of freedom. But there it is. We're going to do another example right now. And by the way, this would be a really good time to pause, try example 2 on your own, see if you can do it without my help. If you get the right answer, you know how to use the t-distribution and you can move on. If you don't get the same answer, that's okay. Just practice again and make sure to watch out for that in the practice problems later on. I'm going to solve it now. On this one, it says our sample size is 22. We're looking for the cutoffs of the middle 98% of the distribution. First, we need our degrees of freedom. That's always n minus 1. So here, that's 21. Easy peasy. 21 degrees of freedom. We also need our tail area. The one tail area, if we've got 98% in the middle, that means there's 1% in each of the two tails. 1%, 98%, 1%, that's everything. One tail area is 1%, and I'm just going to put in here the two tail area is 2%. You don't need both of those. I just want to emphasize that they're totally the same thing. Okay, cool. So let's go look at the table. Degrees of freedom is 22, so I see it here. And my one tail area is 1%. I'm going to highlight it now. You can see it there. That's the same thing as having a two tail area of 2%. And, oh, I forgot. What was degrees of freedom? 21. Here we go. Match them up in the table. That gives you a cutoff of 2.52. Our cutoffs here are plus or minus 2.52. And that's it. That's all there is to it. It's pretty easy to look these things up. It might seem a little weird at first because it does look different than the normal distribution, but it's the same sort of idea. I think the t-distribution is almost even easier to use because it really only tells you the cutoffs that you're interested in. You can just look it up directly and see what they are. Okay. So now that you know how to use the t-table, we can put it all together and make some confidence intervals. Let's do it. The actual formula here hopefully seems fairly predictable. It's just like the one we did last time. Our point estimate is x bar. We're going to use a t critical value. In other words, we're going to look up cutoffs from the t-table just exactly like we did in those examples a second ago. And the standard error stuff over here on the side, we're using the formula for means. So that's, oh, got a mistake here, S. S over the square root of n, pardon me, not sigma, S. The whole point is we don't know what the standard deviation is, so we're forced to use the sample standard deviation. Once you get the hang of it, I think these things are pretty easy. The problem will tell you x bar and S and n. You'll just need to look up the critical value for t on the table, and poof, you got it. Before we do an actual example, there's one last thing that we need to think about. You need to make sure that your conditions for using the t-distribution are satisfied. And I want to remind you of what those are requirements for making these confidence intervals. In order for this stuff to work, you need to make sure that x bar does follow a normal distribution. This is review from before the break. So I want to remind you, there are two ways we might know that. The one that probably comes to your mind right away is the second one that I wrote here. This is the central limit theorem. If we've got a large enough sample size, if n is at least 30, then for sure x bar follows a normal distribution. But also, if you start with a normal distribution, if the original data that you're taking a sample from has a normal distribution, like human height, for example, then you're guaranteed to have x bar follow a normal distribution also. You don't need both of these, but you do need at least one. Either you need to know that your data follows a normal distribution, maybe you could do like a histogram to check and take a look, or you need to have a large sample size. Gotta have one of those. You don't need both of them, but you do need at least one. So in other words, if you've got a small sample size and your data doesn't follow a normal distribution, or you just don't know what the distribution is, then you're dead in the water. You can't do this technique. The confidence intervals are not necessarily going to work. Let's do an example. Oh, I forgot to write it. One moment. Darn, I don't think I can pause. Okay, I'm just going to have to make it up right now. Example 3. What will example 3 be? Suppose we wish to estimate, what do we want to estimate? How about mean resting heart rate of Denison students? We take a sample of, how about 55 Denison students? I am making this up. And find a mean resting heart rate of, how about 64.3. Standard deviation is, oh, how about 5.8. The units here are BPM, beats per minute for heart rate. Construct a, how about 99% confidence interval to estimate the true population mean BPM for students. Here's the thing. We've got sample data, and we want to use this to find out what's going on with the population. So let's do it. It's not too hard. We know almost everything. For this one, I know that x bar is equal to 64.3, and I know that S, the sample standard deviation, is 5.8. And N for this one is 55. By the way, that means that the degrees of freedom has to be 54, because that's just N minus 1. So let's look up our critical value. Since we're doing a 99% confidence interval, 99% in the middle, that means, think about it for a second, how much is left over in those two tails? Pause if you want to. 0.5%, right? 99% in the middle. Both the tails together have 1%. So the one tail area is 0.5%. There's 0.5% in each one. Okay, cool. Let's take a look. Degrees of freedom, shoot, what did I say? 54. Degrees of freedom is 54. Oh, this is a good example. If you look at the table, do you see where I'm highlighting? Our table doesn't have 54 exactly. That's okay. If that ever happens, just use the next smallest degrees of freedom. If it's ever not there exactly, just use the next smallest one. It's probably going to be pretty close. Don't use the bigger one, because we don't want to assume a larger sample size than we've got. Make sure you always take the next smallest degrees of freedom to be more conservative. So I'm going to use 50 in this case. And our tail area, we're going to be looking at the very end. There's 0.5%, in other words, 0.005 in each tail, and that gives me a critical value here of 2.68. Our t equals 2.68. And that's it. We've got all the information we need now, so let's plug and chug. What's that give me? Our formula, just to remind you, the formula for this stuff is x bar plus or minus t times s over the square root of n. We know what all of those things are. So let's do it. I'm going to do the minus first and then the plus. That's 64.3 minus t star value is 2.68. My standard deviation is 5.8 divided by the square root of 55. Be careful here. That really is n, not the degrees of freedom. It's kind of confusing because you need to use the degrees of freedom to find the t value, but for the standard error, you're just going to use n. Okay, cool. That gives me a lower bound of 62 something. And I'm just going to copy paste to get my upper bound. Let me label these things. This one is the upper. And this one was the lower bound. So altogether then, we are 99% confident that the true mean heart rate of Denison students is between 62.204 BPM and 66.396. How about? The end. We've taken the sample result. We know we don't expect it to be dead on the money, but using the margin of error, we've constructed a confidence interval of reasonable values. We're 99% confident that the true, for realsies mean, heart rate of Denison students is somewhere within that range. So the t distribution takes a second to get in your head, but other than that, the technique is very, very similar to what we've seen so far. And I think with a little bit of practice, you guys won't have any trouble doing these things. I'll put some practice problems in the description for the video as usual. Take a look, try them out. If you can get the answers, you'll be good to go for Friday. All right, guys, that's all this time. See you then.